Hello, everyone. Thank you so much for coming so late on the first day. I'm sure you're all knackered. Don't worry, this is really easy. It's a super technical talk, so I hope you've all had some tea or coffee or something. So this is going to be all about Rust, Rust 101, understand the hype. What I'm trying to get across here is I'm not going to go, this isn't a tutorial or a workshop. I'm not going to go great detail, great depth on actually how to write Rust or the exact syntax. We'll go a little bit over the basic syntax, but the thing I really want to get across is understand the hype, is what is unique about Rust, what is different. If you're like me, a few years back before I started studying Rust, you would probably know some people who ramble on about how great Rust is, seen a bunch of headlines popping up here and there, but you may not understand what it is about it that's novel, that's interesting, why people are excited about it, and that's what I want to get across with this talk. So Rust programming language is a compiled systems programming language with a focus on performance, security, and safety. Those are the three main principles set out by the language designers. It also has a very cute mascot called Ferris. He's a Rust-ation. There you go. It's a multi-paradigm language, by which we mean it has a number of functional features, but not really enough that you'd call it a functional programming language. And it's not an object-oriented programming language either, but it does have a number of object-oriented features. So it sort of falls a little bit in between both camps. It is not garbage collected, but it is memory safe, and we'll get into more detail about how that works later. We can think of it more as a competitor to C and C++ typically, rather than necessarily to C# and Java. That is, a lot of the applications we're seeing for Rust today are things that would traditionally be done by C and C++. Less so in the web development space, but the purpose of Rust is very much open. The language designers are very clear. They see it as a general purpose language. It isn't just for writing kernels and drivers. So the best way to explain Rust is with comparison to other languages, right? Now, this diagram, let's not worry too much about the details, the finicky of whether Java is faster or slower than C# or whatever, what have you. But if we go with the general gist of this broad diagram as we have it, we have y-axis showing us the performance of some given tool, and assembly, of course, is about as close to bare metal as you can get, but it doesn't give you any safety. You don't have any type safety, you don't have any memory safety, you're just out on your own. And so in the x-axis we call safety, it's way along on the left. And as you get a bit further along, we've got, okay, C and C++ offering you a bit more safety, maybe a bit less performance. And then way down here, we have the garbage collected languages like Java and C# and the interpreted languages. And historically, this has been the trade-off, right? This diagonal line here between garbage collected and non-garbage collected languages. The kind of rhetoric was that you could either choose a fast language with less safety or a safe language that's less fast. The aim of Rust is to break up that dichotomy by offering a language that is as performant as C and C++, or at least in the same ballpark, and as safe, if not safer, than languages like Java and C#. It does this in large part by offering memory safety on the same degree that you would expect from Java C# without offering runtime garbage collection. So it cuts out this whole runtime garbage collection aspect by which Java and C# and interpreted languages as well are intermittently at your runtime checking to see which variables are, or which values in memory, I should say, are still being used, and then cleaning them up if they're not being used, which is a somewhat intensive operation that causes performance impacts. Although it has to be said, of course, if you just know how to write good performant code, it will always make a bigger difference than whether or not you have garbage collection. Now, a few other features of Rust. So like we said, performance comparable to C and C++, not garbage collected. It has a very, very strong type system. So this is a pretty major feature of Rust. A lot of things that you might see represented in different ways in other languages are represented using the type system in Rust. It's very, very robust. There is a sort of overarching aim or design direction in the language to move as many errors that the user might encounter as possible into compile time. So face the developer upfront with a complexity that would later cause the user issues down the line, and have you face and solve these problems rather than overlooking them and allowing the user to potentially be hit by these things when it's deployed. It has a number of systems programming features, so you have direct memory manipulation, you have interoperability with C and C++, and this enables it to be used for all sorts of things like embedded programming, drivers, operating systems. You have fearless concurrency, so along with the same robustness features that make Rust very safe to use, it also has a number of features that make race conditions extremely unlikely and make it much more safe and secure to use with multi-threading and asynchronicity. It also has really friendly, comprehensive tooling. In a lot of languages, you get the programming language up front, someone develops a programming language, and then somewhere down the line, someone else will come up with a package manager and kind of bodge it on the side of a language. With Rust, because it came along a bit later and has the opportunity to learn from other languages, all this stuff is built in, first-party package management, tooling, everything built by the same group of people. So applications for Rust, where would you use this language if you were to go out and get really excited about it? Well, anywhere where performance and safety are key considerations are good applications for Rust, I would say. So game engines, operating systems, file systems, web browsers. I also think anywhere with safety critical software, so anywhere where a failure, fault in your software might cause real harm to human people is a really good application for Rust. But there's a lot of stuff out there. I was talking to someone just last night about they were discussing plane tickets, right? And that occurred to me pretty much as we were talking about it as an ideal use case for Rust. You want it to be instantaneous, you don't want to add any latency to the user experience, but you also want to be damn sure you're correct, because if you make a mistake, that's going to cost potentially your employer a whole lot of money and inconvenience a whole bunch of people if you sell the same ticket twice or something. Okay, so getting a bit more into nitty-gritty. I always feel like if you learn a bunch of things about a programming language in the abstract, it's different to materialize it in your head until you actually see what is the thing we're talking about, right? So here's the hello world for Rust. You have functions defined using fn. Otherwise, it looks pretty similar to any C-like language, right? If you know Java, Python, C#, C++, anything like that, this probably looks immediately very familiar. Semicolons at the end of a line, curly braces denote a block. And there's one funny thing about this, which is that we're calling a function and using an exclamation mark at the end of a function name. Don't worry about why that is. It's beyond the scope of this talk. We're not going to get into that. Just know that certain functions you have to call with an exclamation mark. So basic syntax beyond that, you have your loops, kind of similar to Python. You can do for x in y, and you also have ranges. So you can say for I in x dot dot y to loop through a range of numbers. Your if conditions look pretty much as you would expect, just you have no brackets around them. The language designers looked at the brackets that you see in a lot of programming languages and just said, why are they there? They don't really need to be there. There's no reason the compiler really needs them to be there. Let's just simplify it. And then arithmetic is pretty much the same as any language. You use the keyword let to define a variable and equals as an assignment. Your tooling, you have tooling called Cargo, which handles pretty much everything you would like within Rust. So you can create a new project using Cargo new. This is your equivalent of Gradle or NPM or the .NET CLI, anything like that. When you create a new project, it's very, very simple. You just get your cargo toml, which is the equivalent of, let's say, your Gradle file or package.json. It just contains your project information, and you get one source file. Nothing complex going on at all. The only other thing of interest is that if you have Git installed, it will automatically install or prepare a Git repo in the same directory. Your cargo toml looks a little bit like this. So you just get some basic information about the package, and you can list dependencies here that cargo will automatically download and make available for you. And then you can run it with cargo run. Those are all the fundamentals of actually running of writing a program in Rust and experimenting with it. A few other features that are worth knowing about the syntax. We have types and we have inference. So you can specify a type for a given variable with a colon. So here we're saying A is a unsigned 8-bit integer, but B, we're not specifying the type at all, and we're just saying it's 1. In this case, the compiler will infer that this must be a number because, well, we're assigning it a number, and it will default to a 32-bit signed integer. However, it does go a little bit cleverer than that. It doesn't go quite as clever as things like F# that have really advanced inference, but it will do, say, if I define a function that expects a 8-bit signed integer and I pass B into that function, the compiler will figure out that, oh, B must be an 8-bit signed integer, and then infer that type back to its definition. Variables are immutable by default. So when I declare a variable with let, if I then try and modify it, it's going to complain at me. If I specify mutable, however, so the mute keyword, MUT, then I will be able to change it. If I try to compile this program, what I'm going to get is this error here. Now, I talked a little bit about how good the tooling in Rust is, and this is a really good early example of that. It's not just giving us an error message on an individual line like most compilers would, saying, error of this name has occurred on this line. It's gone a little bit further, and it said, okay, the error is that you cannot assign twice to an immutable variable. It's occurring on this line 6 here, but actually it's also traced back where that variable was declared, and it's telling us, okay, the error really begins on line 2, and then it's giving us a comment saying exactly what we need to do to fix this, saying, you can just add the mute keyword here, and then this won't fail to compile anymore. You have shadowing in Rust as well. This is not common in a lot of other languages. Shadowing is a little bit of a controversial feature. It can be problematic in making readable code, but there are good reasons specifically why shadowing is useful in Rust. By shadowing, I just mean that if you declare 2 variables of the same name, the second one will shadow the first. Within the scope of these variables, you'll only be able to identify the later one you declared that shadowed the first one. In Rust, just about everything is an expression. So this is really interesting, right? In most, well, in all programming languages, you have either statements or expressions, where statements don't necessarily evaluate to any particular value, but they do something. They perhaps modify state, they have some kind of action, or they change control flow. Whereas expressions have a value. They are things that actually evaluate to a given value in memory somewhere. And in Rust, you have very few statements. Almost everything is an expression, which has some interesting implications. So here we're saying let A equals true. That's just a statement, a let statement, and we're assigning the expression true. Then when we say let B equals if, well, ifs, I'm so used to calling them if statements because they are statements in every other language, but in Rust they are if expressions. Ifs are expressions, so we're able to assign one to a variable, and that has all sorts of interesting implications in turn. So in the second example, we're defining a function, and a function in Rust is really just a block that has a contract associated with it, right? A block in itself is a generic construct in Rust. So anywhere where you see 2 curly braces and a bunch of code in between them, that is a block. And all blocks are expressions. So functions, therefore, are expressions. We decide what the value of a block is based on the last expression inside the block. So whatever that last expression is inside the block will be the value of that block. In this case, we have an if expression, which is the last thing inside that function, and therefore the result of that function will be the result of this if expression. This is just a really neat thing about Rust. You You can use a return keyword if you like, and there are some instances where you'd like to, but by and large, most people intuitively use this method for returning variables or returning values. So that was the basics. Now, I said I would show you what's interesting about Rust, what really makes it stand out and is different. And a big part of that is ownership. This is probably Rust's most unique feature, and it is what enables Rust to have memory safety without having garbage collection. So in short, we just know that when a variable goes out of scope, it is going to be dropped automatically. Specifically, the compiler is going to automatically drop a line into your compiled code for you that says, drop this variable from memory. That's all ownership really means, but in order to achieve that, we need to do certain things. So what do we mean by scope when we say a variable goes out of scope? Well, we're talking about blocks. Any of these instances, say different functions, are scopes, and we can also arbitrarily declare blocks anywhere we like inside a function, and that would be a scope as well. And when we say something is in or out of scope, we can say here that B is out of scope on line 3 because it hasn't been declared yet. B is then declared on line 5, and on line 6 we can say it is in scope, and that's why we're able to do some changes to it. But when we get to line 8, the scope that B was declared in is closed, and so B is out of scope, right? Now, the interesting thing about ownership is this piece of code here, right? We are assigning a string to a particular variable, but then we're declaring a new variable and reassigning that first variable to this new one. What's going to happen here is that it's going to be very unhappy. It's going to complain to us, and the compiler is going to tell us that we're trying to borrow a value that has been moved, okay? And what the heck does that even mean? What this basically means is that we're doing something that is preventing the compiler from being able to clean up our memory for us. We've violated what it calls the ownership rules, which ensure that the compiler is safely able to clean up the memory after we've left it. Now, it's worth noting that this doesn't happen necessarily to all variables. So in this case, if we do the same thing with an integer, it actually works fine. And the simple answer for why that is the case is that integers are stored on the stack, strings are stored in a heap, more or less. We can hand-wave the complexity of that away. And variables that are stored on the stack are copied, so they aren't affected by this. But that's a whole lot of jargon, so we're going to go into a bit more detail to make sure everyone understands. I did say this talk would be appropriate for beginner programmers, so I'm not going to assume that everyone is super familiar with how the stack and heap memory models work. Of those of us who are familiar with it or who have studied it, it's probably been a long time since you last had to really think in great detail about it. So let's go over what we mean by stack and heap. So the stack, if you've ever seen a stack trace, the stack is essentially that. When you go through a stack trace, that is the stack memory model popping layer by layer and tell you where it's been. In this example, we have a function, a main function that's calling a second one. And when we enter this first function, we're going to allocate a piece of memory. For this variable, we're calling x at some address. And this is what we call a stack frame. So as soon as we enter that scope, we're creating a new stack frame in memory. And when we enter a new function, we're creating a second stack frame for this new function. We're able to tell which ones are part of which stack frame, and therefore, when we leave a function, we just pop the top stack frame, and then all the memory allocated to that function is gone. And similarly, when we end the main function, all the sort of root stack frame is popped, and all the memory ever allocated to the application is gone. So that's really neat, pretty intuitive, pretty straightforward, clean. It doesn't really raise any problems, right? So why is memory so difficult if the stack is so simple and clean? Well, that's because the stack can't represent certain object types or certain things we'd like to do with programming languages we can't do with a stack. So we can't represent tree structures and other complex object structures with a stack, and we can't really handle multi-threading, for example. And for all of those things, we have the heap. Now, the heap is a very different memory model in which you can more or less assign any piece of memory to any address, so long as you keep rough track of which ones you're assigning where. And that is exactly why one of these examples work and the other doesn't. When you're reassigning a value on the stack, you're just copying it onto a new stack variable. But when you do it on the heap, something more complex happens. So let's re-examine this example, right, and look in the heap memory model, this other way of thinking about it. In this example, we're just assigning a value in memory to a variable. And what happens here is that we get one value on our stack, which says, okay, I have a pointer to a space in the heap. And then we can follow up that value and say, okay, the value of this is hello, by finding it in the heap and going forward the right number of indexes, yeah? But what happens in this case? It's really not obvious what the right thing to do here is, and depending on who you ask, they might have different assumptions about what should happen here. So there are generally two ways to handle this. You can either copy the stack variable, so that's the pointer, and then you have two pointers to the same space in the heap, yeah? The problem with that is what happens if I delete one. Now my value in the heap may have been removed, but I still have my previous variable s1, which is pointing to the same place, and this is a dangling pointer, and this is a cause of an enormous amount of frustration and a lot of security vulnerabilities, because it would allow you to either delete things in memory that you shouldn't be able to delete, or to view things in memory you shouldn't be able to see, or to cause all sorts of undefined behavior and crashes. There was a report from Microsoft a while back. I think it said something like 70% of all security vulnerabilities they study are the result of exactly this sort of memory problem. Now, the other option is that you can duplicate the actual value on the heap instead. So now you don't have a dangling pointer, because if you delete one, the other one will still be there. But there are a couple of big drawbacks to this as well. One is that it's just counterintuitive, right? I think a lot of people in here at this conference are Java programmers, so you're used to the idea of passing by reference, right? So passing by copy just wouldn't feel intuitive and might lead to confusion. The other side is just that it's very, very unperformant. It leads to double allocating a lot of the time and wasting your memory. So what do we need to do to prevent this from happening? Well, Rust has the ownership rules. This is the sort of third option that very few other programming languages have done. The ownership rules, a lot has been written and said about them, but they're really just very simple. Just these three things. Every variable in memory has an owner. An owner is a variable. For a given value, there can only be one owner at one time. And when an owner goes out of scope, the value will be dropped. So every value in memory belongs to a variable. You can transfer that value to a different variable, but it must belong to a variable. And it can only belong to one at a time. And when that owner goes out of scope, the value will be deleted from memory. That's all ownership is. So this solves our problem, right? Because when we do that, what we're doing on line 2 there, we're neither copying the heap, nor are we leaving a dangling pointer, because that first variable essentially becomes disavowed. We're no longer allowed to use or touch that variable because it would violate the ownership rules. When we try to do so, the compiler will punish us for trying to break the ownership rules. And instead, we have the performant copy here, where we're not copying the values on the heap, and we don't have to worry about leaking memory. So that's a whole lot of explanation. We went pretty technical. Don't worry if one or two bits were a little confusing, but hopefully this error makes a bit more sense now. What we're saying here is that we tried to borrow the value from S1, but the value that S1 references in memory is now owned by S2. So we can't use the value from S1 at all because that value has been moved to a different variable. Let's go through a bit more of a practical example. So here we're saying we have a variable S1 we're declaring, and we're assigning it some expression. That expression is calling another function, which is gives ownership. The gives ownership function is going to declare a new variable that allocates some memory, and that memory is just a string, and then it's going to return that from this function. When we get to the end of the scope, the compiler won't delete the value of this variable from memory because it knows that it's being returned from this function, in which case the ownership of this value is moving, and the ownership will move to S1. Then we're creating S2, and this is going to allocate something new in memory and assign it ownership to the S2 variable. Then we're going to declare S3, and we're going to pass the S2 variable into this takes and gives back function. So in this case, we're actually giving a variable, we're transferring its ownership into the scope of a function. I know you can't see the bottom of the screen too well back there, sorry about that. But what's happening here is that we immediately return this value from the function, right? We're not actually doing anything at all with it. You can envision in a more practical example, we'd do some transformation with it, but we're just going to return this value from the function. And what that's going to do is, after having taken ownership of this value, transfer it right back to this S3 value. Now, what's going to happen next when this function closes is the compiler is going to have to decide which of these values in memory am I going to remove, or which commands do I inject into this function to ensure that all the memory used in this function is cleanly freed. When it looks at S3, it's going to say, okay, S3 has gone out of scope, and it is an owner of a value in memory because that takes and give back function transferred ownership to S3. Therefore, we're going to free that space from memory. When it looks at S2, it'll say, actually, the value that was allocated to S2 has been transferred to a different variable. Therefore, there's no value that belongs to S2, so we don't need to free anything. And then when it goes to S1, it will recognize that this gives ownership function transferred ownership to S1, so it needs to free the memory allocated to that. So again, hopefully this makes a little bit more sense why you're getting this error that confuses a lot of people when they start Rust. I think it's worth going into considerable detail to make sure people have a confident understanding of this. It is the most novel aspect of Rust that people often take an interest in, but it can also confuse beginners a lot of the time as well and frustrate people if you don't know why it's happening and how to handle it. Regarding how to handle it, well, the ideal situation is to refactor your code so that you're not trying to reference a variable that you shouldn't be, one that's transferred its ownership, right? But if that's not possible for one reason or another, there are a few other things you can do. Like you can clone a variable. So if you decide to use the clone function, you are explicitly telling the compiler that I'm going to take the cost of reallocating this memory. I'm going to clone it on the heap. And you can also use shadowing, which we discussed earlier, right? So I can just say, all right, maybe I've passed the value of S1 to some function that's performed a transformation, and then I want to take it back again. But actually, I don't want to treat this as a new variable. I'll just name it S1 and treat it as the same variable I was looking at before that I've effectively just transferred the ownership back to. This is the reason why shadowing is particularly useful in Rust, whereas in a lot of other languages you wouldn't see it. So, okay, that's the most technical, scary part of the talk. I hope that made some sense. So to summarize, the Rust compiler will automatically clean up unused values from memory for you. I've written variables there, and I should have said values. To enable the compiler to do this, we have to follow the ownership rules. And if we break the ownership rules, the compiler will alert you and make sure you fix it before your program can run. Okay, so those that was perhaps the most novel feature of Rust, but there are a number of other ones that are quite interesting. So, for example, in Rust, all strings are UTF-8 encoded by default. This means no more having to encode and decode ASCII to and from Unicode. This, I think, represents a big part of the approach of Rust. There's a lot of these sort of what I would say are common sense decisions around recognizing pain points in other languages and then making language decisions, language design decisions to just eradicate them completely and remove them, right? So you don't need to worry about whether you can support the right alphabet, encoding into this or that format. Everything is UTF-8 by default, and that removes a whole classification of problems. You have enums in Rust. They're quite an important feature. They are algebraic data types similar to F# or Haskell, so they're a little different to enums in a lot of other languages you may have seen. Unless you're a really enthusiastic functional programmer, then you might know exactly what I'm on about already. An enum has a number of variants, but each variant can contain different data types. So in this example, we're implementing the command pattern, and we have a message that presumably is going to some program that is going to respond, and that message might be to quit, in which case we don't need any more information, just exit the program. Or it might be move, in which case it needs some XY coordinates to move to, or we might be writing a message, in which case we need a string, and so forth. These enums are a really, really common, consistent pattern you've seen in intuitive Rust. A lot of Rust programs are formatted like state machines that transfer between various different states, and a lot of that is done by combining enums with pattern matching. Rust has very, very advanced pattern matching. You can do all sorts of funky creative things with it, but the key thing is that it's very easily readable and understandable, right? So in this example, we're saying if it's a pineapple or if it's a strawberry, it does not belong on a pizza. And controversial, I know. And it's very, very straightforward to read that and just say, oh, okay, if it's that state or that state, it goes to this outcome, right? But you can also do some fancier stuff. So, for example, this second one here is showing us that we can use characters as ranges through the alphabet. You can do all sorts of things that are really neat and really easy to read using pattern matching. If you've not come across pattern matching before, think of it like a really fancy switch statement. Oh, and pattern matching is ensured to be exhaustive by the compiler, which is quite an important factor. So if you were to say match on an enum and then later add a new variant to that enum, the compiler is going to warn you, or well, actually error in every instance where you're matching against that enum to tell you you haven't included this arm that needs to be here, you haven't encountered for this possible use case. Which again is a big part of the safety and robustness features of Rust. Talking of safety and robustness, you have no nulls whatsoever in Rust. The billion-dollar mistake, as it's often called. Nulls cause all sorts of trouble every time you have any variable passed to you. You can't actually trust it, right? You can't take it for what it is. You have to say, it could be an integer, or it could actually just be a null. And you have to add all sorts of extra verification on top and all sorts. Rust does away with that whole problem, and instead it embeds the idea of something being or not being there in the type system. So this is an option type. Anyone from Java will know what an option type is, right? But we match it with our pattern matching, so we can make very simple readable code like this and say, okay, we're making a query to the database, and we're going to match on the result. If there is some result, then we'll render our cool page. If there is no result, then we'll render a 404 page. And in the case that a function might throw an error, we don't have any exceptions. We don't have any try statements. We don't have any catch statements. Again, what we do instead is we embody this problem in the type system. So we have an error type that works similarly to the option type, but if there is nothing there, it can also provide an error. This is a big part of the whole approach of Rust, that I think really simplifies things. So instead of having multiple different concepts to handle multiple different problems, you just have this one very simple idea of a type system, and you can handle lots of different problems with just the type system. No need for concepts like nulls and exceptions and try-catches and so forth, if we can just embody all these concepts in the type system, and the type system is very, very strict and safe and ensures that you're doing everything correctly. I mentioned before there are some object-oriented features. Rust has traits and structs. So structs you can think of as being similar to classes. They're objects that contain multiple values, and you can attach functions to them, act on these values. Traits you can think of as similar to interfaces, but they do some other quite interesting things. So in this example, we are creating a summary trait, and then we can implement the summary trait for both a news article and a tweet, and then treat them the same and just know that, okay, what I'm passing into this function is a thing that can be summarized, and we don't care whether it's a news article or a tweet. And that's generally how we handle that problem. Other than, outside of this, we don't have any of the typical object-oriented features you might expect. We don't have inheritance. We don't have polymorphism. What you have instead is traits. Okay, so, wow, I've buzzed through that in pretty fast time. So, in summarizing Rust at a glance, we have this whole philosophy, this approach of moving as many errors as possible from runtime into compile time. So the developer should be faced up front with any problems and have to solve them before the code is deployed, instead of the user one day hitting that problem. We try to maintain top-level performance while doing this, not sacrificing performance to achieve it. And we have great tooling for really painless, very productive developer experience. So, sounds great. Maybe the future is Rust? Maybe? Who really knows? But Rust has been the #1 most loved programming language on Stack Overflow every year since 2016, which is pretty awesome. It has its own foundation now, so it's independent from Mozilla. All sorts of different organizations are represented in the foundation that have an interest in driving Rust. It's all handled really, really transparently and openly. A lot of good folks involved, and the future of Rust seems to be in really good hands. There is support for Rust. Rust has been added to the Linux kernel project, so Rust is now the only language other than C that has been trusted to actually modify the Linux kernel, and I think that's a really strong testament to the sort of trust it's gaining. It's also become part of Windows, Android, and Linux, and many companies like Google, Apple, and Amazon are investing in Rust and writing all sorts of software in it. It's also been endorsed by Ed Snowden for its security features. I sort of glossed over security just for a limited time, but suffice it to say that the same sort of features and approaches that enable Rust to be very robust and safe also give it very strong security features. It wouldn't be fair of me to stand up here and ramble about how much I like Rust if I didn't also talk about what some of the drawbacks might be if you're seriously considering investing in Rust, in the ecosystem and the language. So a few things are that it's quite a young community. I mean, it's over 10 years old now, certainly, but it's relative to other languages still has a fair bit of maturing to do, right? It doesn't have the big built-up extensive libraries that Java and the like have. There are increasingly a lot of really interesting languages written in frameworks and libraries written in Rust. But a lot of the big ones are still not really in a production-ready state. They're still in a 0-point-something state and carry certain caveats around. If you're going to use this, don't expect a great deal of support, and perhaps it's best to hold out until we release a production-ready version. There are many fewer developers in the job market as well for Rust. So if you're starting some great new project, that might be a concern. Have a think about how you're going to find Rust developers. At the same time, I feel like it's worth mentioning there are quite a few Rust developers who complain about there not being enough Rust jobs. So if anyone ever figures out how to find all the people who complain about there not being enough Rust jobs and all the people who complain about there not being Rust developers and get them to talk to each other, you'd solve a great problem. It is also more complex than other languages. I think this is a bit of a controversial point. I think a lot of people outside of the Rust ecosystem will exaggerate how complex Rust is. Once you learn it and get programming with it and practicing it regularly, you will barely notice the ownership rules are even there. But at the same time, I do think some people inside the Rust community do the opposite, right? We have a tendency to downplay the complexity. But I think it is fair to say that if you compare it to a language like JavaScript, obviously Rust is more complex, and there's a chance that it may take longer to train new developers in a language like Rust as opposed to a simpler language with a lower barrier of entry, right? These are all the sort of things you need to keep in mind if you're considering investing in Rust. And lastly, it has longer compile times when compared to some of the compiled languages, because all the safety elements we talked about, all this robustness, all these additional checks, all that incurs a cost at compile time, going through thinking about all these things. So if you are so hyped about Rust now and you thought this talk has lit a fire inside your soul and you just want to get out there and do it, then the thing I would recommend is to start with a Rust book. This is a free online book. You can just Google it. It's written by the language designers themselves. It's very frequently up-to-dated. It's really, really well written, honestly. It was a place I started, and I really enjoyed it. I got together a group of friends, and we all went through it chapter by chapter and, compared notes. It's a really, really good way to learn the language. I would also recommend Exercism. So this is a sort of online programming challenge website. You've probably seen similar ones. You can go online and find a particular challenge and solve it in Rust. The thing that makes Exercism different is that it has a load of these volunteer mentors who will actually look at your solution and give you feedback and advice and say, okay, that's good, but it would be more intuitive, it would be more Rusty to do it this way, or have you considered this feature of the language? There are a few other books like Zero to Production and Rust in Action that are really good ones to follow up on as more intermediate level. There's some good YouTube if you're more of a video learner. Let's Get Rusty is a well-recommended beginner series for learning Rust. And there's also Crust of Rust, which is a much more advanced but really interesting deep dive into Rust concepts. And lastly, I would really recommend getting into the Discord groups that exist around Rust. There's an official Discord, there's an unofficial Discord, there's a video game development Discord, there's I think 2 video game development Discords. Whichever ones you choose to join, I find them really, really helpful. Whenever I'm stuck on something with Rust, with one of my projects, I jump on there and have a chat. And there's always a bunch of really enthusiastic folks happy to help you out and offer advice. Okay, that's all I had. Thank you very much, Devox. We have 7 minutes if anyone has any questions you want to ask about Rust. Otherwise, I'm happy to let you get down to the pub or whatever it is you're doing this evening. Shoot. Oh, that's you, it's you.
Okay. So, you were mentioning that the online Rust book is updated. This means that the language is updated. Are these changes is it backward compatible?
Yes, good question. So in Rust, we have a concept of additions. So there are frequently changes to the language in various ways, but they are only additive unless there's an addition change. So whenever we want to actually change this syntax significantly in a way that would modify backwards compatibility, what we do is, how many years is that? I think it's every like 2 or 4 years, however many it is. We let those kind of build up until it comes time to release a new edition. And you'll have editions like, I think there's a 2020 and a 2024 edition. But the compiler is always backwards compatible with every edition. So when you start a new project, you just specify which edition you're using, and the compiler will always guarantee to compile correctly for whatever edition you specify. So if you start a project today, you'll still be able to compile it in 10 or 20 years' time using the latest copy of the Rust compiler, and you can choose to upgrade or not to the newest editions as you choose.
Surface level question, but where do you think like the complexity in learning Rust comes from? Like what? Because it feels like there's some beginner concepts, right? It's the ownership, it's the concurrency. Like where do you think like this variety of how complex and hard it is to learn comes from?
It depends on where you're coming from, right? So my journey was coming from mostly a web development background. So for me, some of the biggest learning parts were learning the same sort of stuff that probably a lot of C and C++ developers already know, getting used to using a systems programming language, being much more aware of memory and memory models and optimization. But otherwise, I think the biggest learning challenge is probably the ownership and borrowing, which is another aspect of ownership I glossed over. But honestly, it is something you need to learn. It is an obstacle to overcome, but it's not huge. You just need to read a bit about it, get it in your head, and then most importantly, practice it. Just write a bit of Rust code, let the compiler tell you what you're doing wrong, and before long it'll click and you'll just be doing it intuitively.
In your example with the function takes and gives back. Okay, let's imagine that that function was very simple, just return the same string. Let's imagine that there is a much more complex function. Is there a way that I can know ahead of time when I'm writing the code, okay, I need to call this function, and can I know ahead of time this function will transfer the ownership?
Yes. So this is going a little bit beyond this. It goes into a few things I kind of intentionally omitted for simplicity, but you can do things like when you write your parameters for a function, you can specify whether or not you're going to transfer ownership or not. So some functions, when you call them, if you pass a variable into it, you'll actually be transferring the ownership into that function. Other cases, you'll just borrow, in which case you're leaving the variable and the ownership where it is, but the function can reference that value in memory as if it were a pointer. So that's generally, yeah, it's made very, very obvious just by looking at functions whether or not you're going to transfer ownership. And then, of course, there are cases where you might pass two different variables into the same function, and maybe one of them gets returned and transfers ownership back and the other doesn't, and that might involve a condition, so it might be decided at runtime. And when that happens, we have to look at lifetimes, which is another can of worms, but again, just something you learn and get used to that helps to resolve that situation. Does that answer your question?
Yeah, I will have to look at some examples to understand. Yeah, thank you.
Cool. Oh, go ahead.
So you showed some demonstrations of the type system, which is very strong. Showed some like the integer bit length stuff, that sort of thing. Can you define any custom types? Do like what's called refined types in Scala? So, for example, an uppercase only string.
I don't think you can necessarily do uppercase only strings. You can do aliases. You can do things like you want to redefine an 8-bit integer as, we'll call it a meter, and then make sure that, like, if I pass a meter into its function, someone else doesn't pass a yard in, and then they don't get mixed up. You can do things like that, and you can do fairly complex stuff with I forget the right phrase. I think we call them new type objects or something like this. But you can build these objects that wrap simple values and then embody functionality around them to ensure that when they're initialized, you're passing in the correct values. But I don't think it's quite the same as refined types in Scala.
Oh, okay. But if you could run validation at the beginning, you could validate whether it's uppercase or not, or it's not an important example.
But depending on what you mean by the beginning, like it would be, Yeah, like when it's initialized, yes, yeah, you can do things like that, certainly. Yeah, you could have a object that wraps an integer and behaves just like an integer in just about every way, except that you have to call a particular function to initialize it, and that might return an option that either will be there or won't be, depending on whether what you've passed is valid. Any last question? Oh, go ahead. In real-time embedded, there are a bunch of stuff happening in embedded systems. Rust recently became certified for use in the automotive industry, and there's a bunch of stuff happening there with people embedding Rust into cars now and other safety-critical systems. Yeah, definitely a lot of stuff happening in the embedded space. That's all the time I have, but feel free to come up or just find me around the conference. Oh, I also have a bunch of stickers of Ferris. If anyone wants a sticker, come chat to me. I'll give you a shiny Ferris sticker. Otherwise, I'll put them in the sticker table tomorrow. Thanks, everyone.